Continuing in 7.2, let's look at existence of Laplace transform. Before we get to that directly, let's talk about a few definitions. First one is jump or removable discontinuity and what that means. And then we'll look at piecewise continuity, all of which you may have seen before. Okay, so a function, but we'll just go ahead and define it. So a function f of t on AB has a jump or removable, well, actually jump, as a jump discontinuity at t naught in the open interval from a, b, if f of t is discontinuous at t naught, basically it doesn't like approach infinity, right? So it jumps. But it doesn't like take off to infinity or negative infinity. So what you have to have is the limit is a finite number. So the limit of f of t as t approaches t naught on the left equals a real number, and the limit of f of t as t approaches t naught on the right equals a real number. So both exist and are finite is the idea. So it doesn't like approach infinity, right? So it exists, but it can be a different number. Like you can go to here and then to here. That's a jump discontinuity, but they both exist as a limit. Function value doesn't have to exist though. All right, so that's one of the concepts. Next one is piecewise continuous. Piecewise continuity. You would have seen this, well, I don't know, a number of places, but Calc 3 you would have seen this. So definition, a function f of t is piecewise continuous on AB if f of t is continuous for all t in AB, except possibly for a finite number of points. So except possibly for a finite number of points f of t has a jump discontinuity. So basically, it could look like this. Let me draw a picture of that. So you could have, you know what, let me grab it. It's just really, really good. Sometimes it's just easier to show you the picture when it's really nice. Sometimes it's better to draw, but in this case, it's not a big deal. So there's a good picture of something I drew earlier. So you're on A to B right here, and then these are the jump discontinuities, and it's a finite number like that. There's other definitions that for integration that you can define. So basically an integral will still be defined as long as there's a finite number of discontinuities. So you could be a bunch of discontinuities and this integral is still defined. It's only at a point though, right? It can only be at one point. So it can't be like a break of an interval. So there's your t naught like that. But what you have, though, is there's also another way of describing this for a integration, that it can actually be defined, because we're talking about integration eventually, but it actually could be defined at a, we call a countable number of discontinuities, basically equivalent to the natural numbers or integers. Those are countable sets. And it gets kind of weird when you talk about infinities like that, but that's what you can look at. Anyway, this one is just a finite number. We'll stick to that. Okay, moving along. And this is just some more kind of notation stuff that says the same thing. So a function f of t is piecewise continuous on 0 infinity if f is piecewise continuous on 0 to n for all n greater than 0. So that's another way to describe what we mean by infinity. So you go to a value, a closed interval, but then it's true for any of those values, which means essentially it just keeps going as you approach infinity. Okay, now let's talk about convergence of the integral. So this is integral convergence. Okay. So to talk about integral convergence, I want to remind you of basically the idea of sequence of series. Like when did we have series convergence? So recall, because remember an integral is really just a summation, right? It's a limit of a sum. Okay, so we're going to talk about summations first to recall some of those concepts. So recall series convergence. And remember, I don't know if you remember this, but back you had a series called the harmonic series, 1 over n. That diverged versus basically a p series with p greater than 1. So we had this, so basically this one, and you're going to approach infinity on both of those. Your starting point doesn't really matter. I mean, it has to be defined. It can't be 0 and all that, but so you often you just put an in right there and it doesn't really matter where it starts. It has to be defined. So this one diverges. That's called a harmonic series and it diverges. This one converges. And we defined a p series where it's 1 over n to the p, and then basically if p, it converges, or we say it's less than infinity if p is greater than 1. You can prove that using the integral test. And so, and it has to do with how fast something converges or diverges. So 1 over n, goes like this, right? But it just doesn't do it fast enough. And that's not really mathematically true, but that's how you can think of it. It has to converge quickly, and then that sum will converge eventually as you approach infinity. Same idea for integration. Okay, so let me write up some of that stuff I just had. So it has to do with how, quote, fast, so the integral convergence has to do with how fast, quote, the graph the function itself approaches the x-axis. So we're going to be looking at functions, and then it's going to, you're looking at e, so it's going to decrease like that. And then but if you multiply by other functions of e, it may not approach it quickly enough. So that's kind of the problem. Okay, where was I at? Okay, I wasn't done yet. Or what we call growth of a function. So fast or growth of a function. So we call this the order of the function. So there's different orders. So there is what we call linear order. We have polynomial order. So I can only grow so much regardless of how large the power of x is. We have exponential order. Okay, and the order of it is denoted by alpha. So like you'll say linear order alpha, polynomial order alpha. So like polynomial order alpha would be x to the alpha, and probably a variable up there or something like. No, I think that's it. But we're going to talk about exponential order. That's what we're focused on because that's what Laplace transform has to do with. All right, so we're specifically looking at that. We're specifically looking at exponential order alpha. So this is called exponential order alpha. So definition 3 is this. So it says a function f of t has exponential order alpha if there exists t and m greater than 0 such that absolute value of f of t is less than or equal to m e to the alpha t. For all t greater than or equal to capital T. So in other words, eventually the function is less than the exponential. So what I mean by that is it can grow faster at first, but then eventually there's some value of t for which the function will always be less than the exponential. So an exponential function is going to be this guy, right? Let's draw a little better one than that. So the exponential function goes like this. Okay, so and then it'll change depending on your order, right? Alpha and your m. But that's essentially what we mean. So when t is 0, you go through here, so that's m. So whatever is here is m. So that'll be your m value. And then it might grow faster, it might grow really fast, or it might grow slower, depending on your alpha. But that's your exponential. So depending on your alpha. And so your graph could do other stuff. So it could do something like this. But eventually it's less than your exponential. So in here, it's growing fast. Maybe it won't be negative, but that's okay. It's growing fast. It's not a very good picture because it's supposed to be positive, but you get what I mean. Well, I guess I can move this thing. Let's move this over. There we go. Now we're better. Okay. So eventually, it does all weird stuff like a polynomial might do or something, some function, but eventually it's always less than. So this would be your capital T right about here. So after capital T, all your little t's are over here, and it's less than this. Excuse me. Your function is less than this, and it's absolute value. So your function actually might go down, but your absolute value would put it back up here. So it's how quickly it does something. So you're comparing your order of growth to your exponential. Okay. So given that, I have an example. Okay, so for example, let's suppose we have f of t equal to e to the 4t cosine 3t. So f of t is exponential order 4. Alpha is equal to 4, because that's your 4 there. Because you can look at the absolute value, since absolute value of e to the 4t cosine 3t is less than or equal to e to the 4t, right? Because the range of cosine is always between -1 and 1, like that. So if you multiply by e, then it's going to be smaller. So because you can say that, this function has exponential order alpha. All right, so it can be shown. So these functions grow faster. You could have like e to the x. That grows really fast. That's exponential order higher than exponential. E to the t squared, again, that's not that form. That's a power of 1 here. Going back to the definition, right? So the power is 1. So this one grows faster, this one grows faster. Factorials grow faster. So you have a factorial. That grows fast. So all of these are faster. And then, of course, polynomials grow much slower. And a linear, of course, doesn't grow much at all. Okay, so guess what the definition has to do with? Okay, where was I at now?